Want to start the recording? Okay. Okay. Good morning, everyone. So we will welcome to the my fourth session. Uh, we will continue talking about shortest paths. So far we have seen graphs, then traversals like depth first search, and then we saw breadth first search. Then we also saw that breadth first search has this interesting property that the every like if from the source vertex you discover vertices through their shortest paths meaning through the number of edges. One thing that it does not do is the shortest path is counted as a number of edges. So now, what if in a real life situation you don't want to count the number of, let's say, maybe you want to go from place like from your home to work, you wouldn't be counting the number of roads that you travel. Rather, you'll each road will have some distance and then or distance or time taken, and that's what will be your actual traveling cost, right? So to model that, we will use graphs with weights on edges. So all the edges will not have the same weight, and we want to minimize the shortest path, meaning shortest, the one which has a lowest total weight, where total weight is by the sum of the weights of the edges there, right? So that is what we will do now, and we'll see one algorithm for that. It's called Dijkstra's algorithm, and we will just assume that all the edges have positive weights, and further all the edges have integral weights. Okay, so you can all of this can be generalized. Like integral is not really essential, but we are just using it for convenience. Positive is kind of important for Dijkstra's algorithm because negative weights can cause some problems, to this algorithm and in general as also, right? So there are other algorithms that take these into account and fix it, but we'll not be talking about that. So this is one example graph. Like I think we went over this yesterday. Right? So like the shortest path from S to B, I think we talked about it, was like it is not this one because this has weight 11, this has weight 14, but if you go this way, it has weight 9, right? I think this is the shortest path, right? We went over this example yesterday. So now we will see the algorithm. So the algorithm uses a queue, but unlike the BFS queue, this is a priority queue, meaning BFS had a first in, first out queue. So uh, whoever entered first will leave first. Whereas here we have a priority queue, meaning everybody is assigned some priority, and this can be thought of as some ranks or some numbers associated with each person, and then whoever has the least value, the minimum value of that number, you will DQ that person first. So everybody is assigned some priority, and in between you also update some people's priorities. Okay, so then what do we do? So the initialization is similar. So initially everybody has weight infinity, everybody's parent pointer is null, and then you enqueue only the source and you make the D value to be 0. And then you have a set S. Okay. So and then you have a set S, so where the completed vertices are included. So this is the set S is like the black vertices in the BFS. Okay. And you keep repeating this till the queue is empty. All right. So initially, so then what do? You extract the minimum entry in the queue. So minimum entry mean the entry in the vertex in the queue that has the, so initially everyone is in the queue, but only S has the D value 0 and everyone else has D value infinity. Right. Um, so initially the first vertex to be DQ'd will be it is a vertex with a minimum D value. Which is a vertex with a minimum D value?
Yes.
It'll be S, right? Because S has 0 and everything else has infinity. So clearly there is only one unique minimum, right? So and that is added to the set capital S, right? And then what you do is whenever you extract an element and add it to capital S, you look at its neighbors, right? So if a vertex U is DQ'd, you look at its neighbors and you update the D value of all of these neighbors. Right? So suppose U has, let's say, U has three neighbors, W1, W2, and W3. Then you update the D values of W1, W2, and W3 using this formula. Okay, and then you and then you keep doing this, and at the end you will have the shortest paths. So maybe instead of going through the code, we'll just see an example, right? So that will be easier. So this is our example graph. So initially, S has weight 0 and everything else is weight infinity, right? Weight meaning D value, right? S has D value 0 and everything else is D value infinity. Right. So now you do extract minimum from the queue. So S will be, this vertex will be extracted. And then what you do is look at its neighbors. So there are two neighbors, this vertex and this vertex, right? So earlier it had weight infinity, right? So now what you do is you update the weight as follows. So now you check whether 0 plus 10 is smaller than infinity, and 0 plus 10 is 10, so it is smaller than infinity. So you update it to 10, and 0 plus 5 is smaller than infinity, so you update this to 5. Right? So you update it using these, the out neighbors with these values, right? So now, the this has been removed from the queue, so everything else is there in the queue. But now with the four vertices have these values like 5, 10, infinity, and infinity. So now one iteration is done, right? And what we do is we now do extract minimum again. So this vertex will be DQ'd because 5 is smaller than 10, right? And now when 5 is DQ'd, it has three neighbors. This one, this one, and this one. In fact, all the other three vertices are its neighbors. So now, which are the vertices that will get updated? It has three neighbors. How many vertices will get updated with the D value?
All the neighbors of 5.
All of them, because 5 plus 3, so if you look at this vertex, 5 plus 3 is actually 8, and 8 is smaller than 10, so this will be updated to 8. 5 plus 9 is 14, so 14, this will be updated with 14, and here it will be updated with 7. So this is what, so it has three neighbors, and all of these will be updated. And one more thing, we also, whenever we make an update like this, we also update the parent pointer of this vertex, all these vertices. So now, since all the three vertices we updated, we update the parent pointers also to point to 5. So, okay. Now, what is the next vertex to be DQ'd? Or DQ'd or extracted out of the priority queue?
7.
Yeah, the one with the weight 7, because even though, so consider this. So even though this vertex, the top left, the vertex with weight 8 was NQ'd before 7, we end up DQing 7 before 8. So there is like already this change of order you can see in even in this very small example, right? So 7 is DQ'd, and basically it has two outgoing edges, one to the vertex with 14 and one to the source vertex. So how many D values will be updated? 1, 2, or 0? So potentially both these D values can be updated, but how many actually get updated?
0 will not be updated.
This will not, the source vertex will not be updated because 7 plus 7 is 14 and 14 is bigger than 0. So this will not be updated. Whereas over here,
13. So
7 plus 6 is 13, which is smaller than 14. So
that will be updated to 13. Huh?
Will be updated. So now the parent pointer of 13 also will be updated to this vertex. Okay, so I'm sorry I didn't write vertex names here, but I hope you can follow this. Right? Yeah. So
The parent vertex will be updated.
yeah, the parent pointer also will be updated. What I'm saying is that I didn't write like names for the vertices in this example. Like if I had written, let's say S, I don't know, A, B, C, D, then it would have been easier for people to follow. But yeah, so I'll have to we are having to refer to these vertices using their weights because that is the only label on these pictures. That's what I was saying. Okay, so now which is the next vertex that will be DQ'd?
Zero is already DQ'd, so
So the green ones are already out.
already DQ'd.
Yeah.
So
So
okay.
there are only two ones in
Yeah,
the queue. This one
eight.
will be DQ'd, and it has two outgoing edges marked in red now. So which are the vertices that will be updated with the new weights?
5 will not be updated.
Correct.
This
This will
13
not be
will be
updated
updated.
because 8 plus 2 is 10 and 10
Hmm.
is bigger than 5. So this will not be updated. Whereas
13 will
8
be
plus 1 is
updated.
9, which is smaller than
Hmm.
13. 13 can be updated. So this is the end of this
Okay,
is the end
so
when.
in this particular example,
Sure.
the source vertex has never been updated. So,
Correct.
like the vertices who are DQ'd are never been updated. But is an example possible where the D values of the DQ'd nodes can also be updated,
It
or
is
is it
not.
never the case?
I'll just restate the question for so that it's clear. So you're saying that in this example, we first DQ'd the source vertex, late it never got updated. Then we DQ'd this vertex, after which it never got updated. Then we DQ'd this, after which it never got updated. Then we DQ'd this. So now you're asking, is it possible that you end up updating a vertex's
Hmm.
D value after you DQ it?
DQ it, yes.
Or is it just that in this example it so
Hmm.
happened that way? The
Hmm.
answer is it cannot happen in a Dijkstra's algorithm as long as we have non-negative weights, right?
Okay.
Um, as long as we have non-negative weights, it cannot happen. Because what we are doing is we are DQing in the increasing, like we are picking out the minimum.
Minimum, right,
So
right.
whenever we pick out a later vertex, right, um, that vertex already has a higher D value than what was earlier DQ'd. Now, if you want to find a shorter path, let's say 7 was DQ'd after 5. So now, in order to be able to update this vertex, the vertex which is labeled 5, in order to update the D value of this, we should have a path that has like where 7 plus that number should be less than 5. So which means that 7 plus that number less than 5 means that number has to be like less than minus 2, which means it necessarily has to be negative.
Hmm.
Yeah, so this cannot happen in the case of Dijkstra's algorithm. In the case of Dijkstra's algorithm, on a graph with positive or non-negative weights, only when you have negative weights can such things happen. And there we need to do something like we have to basically do some algorithm where such things are taken care of.
Okay.
Okay. Okay, so now we have already updated, we have DQ'd this vertex 8 and we already updated this vertex 9 and that is the only vertex remaining in the queue. So now 9, there is only one outgoing edge which is with weight 4. And even this doesn't change anything because